In this video, I'd like to cover Friedel-Crafts acylation, and this is sort of the more popular cousin of the Friedel-Crafts alkylation because it really doesn't suffer some of the problems that we encounter in the Friedel-Crafts alkylation. And so here you can see that the blue acyl group is being added to benzene. And here again, we can use virtually any other aromatic hydrocarbon we can think of, and we can acylate. And this is once again done in the presence of a Lewis acid. Now, the mechanism is quite similar, but it's not quite the same. Okay, so we start from benzene. And once again, I think it's important to point out that if we add acetyl chloride to benzene, the electrophilic aromatic substitution in this case will not take place. Now, it is true that the carbonyl is a very electropositive center. It's a very, very good electrophile, actually. But it's really not quite good enough for the electrophilic aromatic substitution to take place on any time scale that's relevant. And so what we do is we add the Lewis acid. And as mentioned in the video on Friedel-Crafts alkylation, there's an empty p orbital on the aluminum atom. The aluminum atom has an incomplete octet, and so actually it's very Lewis acidic. And so what happens is if you have the empty p orbital on aluminum and it comes in contact with something that has lone pairs, and the lone pair on the chlorine donates into the empty p orbital on the aluminum atom, and what we generate is this Lewis acid Lewis base complex. And what happens is the lone pair on the oxygen comes down like this and displaces chloride. And so what you actually get is this acylium cation. And this is extremely electrophilic. It's a very, very, very good electrophile. And so what happens, of course, is benzene simply comes and attacks it like this. And what we get is our sigma complex as a reactive intermediate. Draw that a little bit better. And then it rearomatizes via deprotonation. And what we really get then is our product. Like so. And we can say plus AlCl4 plus H. Or you can say plus AlCl3 plus HCl. This is our product. And the nice thing about Friedel-Crafts acylation is that there are no carbocation rearrangements possible, as there are in Friedel-Crafts alkylation. And so you don't really see the complex mixtures that you can see with Friedel-Crafts alkylation. The other thing is if we actually consider the electronics of what is taking place here, we're going from compound A, of course, which is benzene, to compound B, which is this acylated benzene. And the reality is that compound B is far less reactive than compound A. Why? Because the carbonyl group is withdrawing electron density via resonance, and we can show this like this. And of course, we can also show this moving around if we like, to show that the positive charge can be delocalized around the ring. But the important point is that with a formal positive charge within the structure of the ring, it's really quite clear that there's far less electron density, pi electron density in the ring than there was before. So A is considerably more reactive than B, and what that means, of course, is that the reaction generally stops at B. It will not per acylate. So that's Friedel-Crafts acylation.